This is the video for Part 2 of Section 3.9, Proof by Mathematical Induction. We can use any valid method to prove the induction step in an induction proof. In the preceding three examples, we used a direct proof to prove the conditional statement. We can also use a proof by contradiction to prove the induction step. The procedure is as follows. So we start with the basis step, and for that we need to prove that P of 1 is true. There's no change there. And then second, we have the induction step. And for this, we need to prove for all k and n, P of k implies P of k plus 1 is true. So for this, we'll use a proof by induction. So using a proof by induction, we suppose this statement is false, or equivalently, its negation is true. So the negation is there exists a k and n such that P of k and not P of k plus 1. So we'll suppose there exists a positive integer k such that P of k and not P of k plus 1, that is, such that P of k is true, but P of k plus 1 is false. We then need to derive a contradiction. Now, after proving the basis and induction steps, we can then use the principle of mathematical induction to conclude the statement for all n and n, P of n is true. Note that we are using a proof by contradiction only to prove the induction step and not the basis step. A proof by contradiction is often a good choice when proving a result involving an inequality, as in the next example. So for this example, we want to prove for all positive integers n, the sum 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 over n squared, is less than or equal to 2 minus 1 over n. So this has symbolic form for all n and n, P of n, where P of n is the propositional function shown. And for our proof, we're going to use mathematical induction on n. And so we have for the basis step, we need to show that P of 1 is true. And to obtain P of 1, we need to substitute n equal 1 into the propositional function P of n. And when n is equal to 1, the sum starts with the term 1 over 1 squared and ends with the same term, meaning there is a single term on the left side. So then P of 1 will be the inequality 1 over 1 squared is less than or equal to 2 minus 1 over 1. So this simplifies to 1 is less than or equal to 1, which is clearly true. So therefore P of 1 is true, and this proves the basis step. For the induction step, we need to show for all k and n, P of k implies P of k plus 1, and we'll use a proof by contradiction. So suppose the negation, there exists a k such that P of k and not P of k plus 1 is true. That is, suppose there exists a positive integer k such that P of k and not P of k plus 1, where P of k and not P of k plus 1 are the two inequalities shown. So for not P of k plus 1, we substitute n equal k plus 1 into the propositional function and negate it, which is obtained by replacing the less than or equal to inequality with greater than, strictly greater than. We then need to derive a contradiction. Now the left sides of these two inequalities look similar. However, the inequality in not P of k plus 1 has an additional term, the k plus first term of 1 over k plus 1 squared. Start by adding this k plus first term, 1 over k plus 1 squared, to both sides of P of k, and this will give us the inequality shown. And the left side of this inequality is now the same as the left side of the inequality not P of k plus 1, which is repeated here. And we can now combine these two inequalities using the transitive property for inequalities to obtain 2 minus 1 over k plus 1 less than 2 minus 1 over k plus 1 over k plus 1 squared. And subtracting 2 from both sides, this simplifies a little bit to minus 1 over k plus 1, strictly less than minus 1 over k plus 1 over k plus 1 squared. Now adding 1 over k to both sides, this will move the 1 over k to the left side, so we'll obtain 1 over k minus 1 over k plus 1 is less than 1 over k plus 1 squared. And putting terms on the left side over a common denominator, this will be k plus 1 over k times k plus 1 minus k over k times k plus 1 is less than 1 over k plus 1 squared. And combining the two fractions on the left side, we'll just obtain 1 over k times k plus 1 less than 1 over k plus 1 squared. Now multiplying both sides of this inequality by the least common denominator, k times k plus 1 squared, which is positive, we'll obtain k plus 1 less than k. On the left side, k and k plus 1, one of the factors of k plus 1 will cancel, leaving us a 1 factor of k plus 1 in the numerator. And on the right side, the k plus 1 squared factor will cancel, leaving us k in the numerator. Now subtracting k from both sides of this inequality, we obtain 1 is less than 0. Well, this is clearly a contradiction. So we can write our contradiction as q and not q is 1 is greater than or equal to 0, which is just a basic mathematical fact that we're familiar with. And we've now shown that 1 is less than 0, so that's not q. And so this proves the induction step. And since we've now proved the basis and induction steps, then by the principle of mathematical induction, for all n in n, p of n is true. Now the summation k equal 1 to n of 1 over k squared, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 over n squared, appearing on the left side of the inequality in the preceding example, is the nth partial sum of the infinite series, summation k equal 1 to infinity of 1 over k squared. In calculus, it is shown that this infinite series converges. So this is an example of what is called a p-series, where p is the power of the term in the denominator. In calculus, it's shown that the series converges if and only if p is strictly greater than 1. So in this case, p is equal to 2, so we know that this series converges. Now from the example, the nth partial sum satisfies the inequality summation k equal 1 to n of 1 over k squared is less than or equal to 2 minus 1 over n. Since the series converges, we can take the limit as n goes to infinity in the inequality to conclude that the value of the infinite series satisfies. So the infinite series, sum k equal 1 to infinity of 1 over k squared, will be the limit as n tends to infinity of the nth partial sum, the sum k equal 1 to n of 1 over k squared. And according to the inequality, this will be less than or equal to the limit as n goes to infinity of the expression 2 minus 1 over n, which is equal to 2. So this tells us that the value of the infinite series is less than or equal to 2. So we know that the series converges, the infinite series converges, which means that it equals a finite number. And this is telling us that whatever the value of that infinite series is less than or equal to 2. It doesn't tell us the exact value of the infinite series, however. Now, determining the value of this particular infinite series was a long-standing problem that occupied the attention of some of the greatest mathematicians of the 17th century. It was not until 1735 that the problem was solved by Leonhard Euler, who proved that the value of the infinite series is equal to pi squared over 6. So pi squared is roughly 9, so pi squared over 6 is roughly 9/6 or 1.5, which is certainly less than or equal to 2. Next, we want to discuss the second form of the principle of mathematical induction. So the principle of mathematical induction can be stated in the following more general form, which can be derived from the original version of the principle. And so this is called the second form. Suppose n sub 0 is a fixed positive integer, and suppose S is a subset of the set of n in n such that n is greater than or equal to n sub 0. So this is the set of positive integers greater than or equal to n sub 0. And let's suppose first that n sub 0 belongs to S, and second, for all integers k greater than or equal to n sub 0, if k is an element of S, then k plus 1 is an element of S. Then we can conclude that S is the entire set of n in n such that n is greater than or equal to n0. So S is the entire set of integers greater than or equal to n sub 0. As with the original version, this version of the principle of mathematical induction can be restated in terms of propositional functions. So we obtain, suppose n sub 0 is a fixed positive integer again, and suppose p of n is a propositional function with domain, the set of integers greater than or equal to n sub 0. And let's suppose first that p of n sub 0 is true, And second, for all k greater than or equal to n sub 0, p of k implies p of k plus 1 is true. Then we can conclude that for all n greater than or equal to n sub 0, p of n is true. So that is, p of n is true for all positive integers n greater than or equal to n sub 0. Now the only difference between the two forms of the principle is the domain of the variable n. So our original form, the domain was the set of all positive integers, so that's all integers greater than or equal to 1. And for the second form, we're assuming the domain is a set of all integers greater than or equal to n sub 0, where n sub 0 is some fixed positive integer. So instead of starting with 1 as we did with the first form of the principle, we start with n sub 0. Now we use the second form when the propositional function is only true for integers greater than or equal to some fixed integer. For an example, we want to prove for all integers n greater than or equal to 4, 2 to the nth power is less than n factorial. So this has symbolic form for all n greater than or equal to 4, p of n, where p of n is the propositional function, 2 to the n is less than n factorial. Now note for this propositional function, p of 1 would be 2 to the 1 less than 1 factorial. And this simplifies to 2 is less than 1, so p of 1 is clearly false. P of 2 would be 2 squared less than 2 factorial, and this simplifies to 4 is less than 2, so p of 2 is false. And p of 3 would be 2 cubed less than 3 factorial, which simplifies to 8 less than 6, so p of 3 is false. So the propositional function is false for n equal 1, 2, and 3. We obviously cannot then prove for all n in n p of n. So this is why we'll need to use the second form of the principle. So for our proof, we're going to use mathematical induction on n, and we'll use the second form of the principle starting at n sub 0 equal 4. So for our basis step, we need to show p of 4 is true. So p of 4 is 2 to the 4th is less than 4 factorial. Well, since 2 to the 4th is 16 and 4 factorial is 24, this inequality simplifies to 16 is less than 24, so p of 4 is true. And so this proves the basis step. For the induction step, we need to show for all k greater than or equal to 4, p of k implies p of k plus 1. So we'll suppose k is an arbitrary positive integer greater than or equal to 4, and we'll suppose p of k, which is 2 to the k, is less than k factorial, and we need to show p of k plus 1, which is 2 to the k plus 1, is less than k plus 1 factorial. Start by multiplying both sides of the inequality in p of k by 2 to obtain 2 times 2 to the k is less than 2k factorial. And this simplifies to 2 to the k plus 1 is less than 2 times k factorial. So this gives us the left side of p of k plus 1, namely 2 to the k plus 1, but not the right side. So we need another inequality that involves 2 times k factorial together with the right side of p of k plus 1, which is k plus 1 factorial. So what we can do is say since k is greater than or equal to 4, then k plus 1 is greater than or equal to 5. So certainly 2 is going to be strictly less than k plus 1. So multiplying both sides of this inequality by k factorial, we obtain 2 times k factorial. And that is what appeared in the previous inequality, and this is less than k plus 1 times k factorial. And k plus 1 times k factorial is k plus 1 factorial. So we now have the inequality 2 times k factorial less than k plus 1 factorial. And by transitivity now, 2 to the k plus 1 less than 2 times k factorial, our previous inequality, and our new inequality, 2 times k factorial less than k plus 1 factorial, together imply 2 to the k plus 1 is less than k plus 1 factorial. And this is the inequality in p of k plus 1, so this proves p of k plus 1, which proves the induction step. And since we've proved the basis and induction steps, then, by the principle of mathematical induction, for all n greater than or equal to 4, p of n is true. Now, while mathematical induction is useful for proving summation formulas and inequalities, as in our previous examples, the real applicability of proof by mathematical induction is in generalizing results about two objects to the case of n objects, where n is any positive integer, as in our next two examples. So for our first example, first note that earlier in the course we proved De Morgan's law for sets, which states that for all sets A and B, A union B complement is A complement intersect B complement. We want to use induction to generalize this law to n sets for any n greater than or equal to 2. So that is, we want to prove what is called the generalized De Morgan's law for all integers n greater than or equal to 2 for all sets A1, A2 up through A sub n. The union of A1, A2 up to A sub n complement is equal to A1 complement intersect A2 complement intersect all the way down to A sub n complement. So this has symbolic form for all n greater than or equal to 2 p of n, where p of n is the propositional function for all a1 for all a2 all the way down to for all a sub n. The union of a1, a2 down to a sub n complement is equal to a1 complement intersect a2 complement intersect all the way down to a sub n complement. Now note that the propositional function includes the universal quantifiers on the sets a1, a2 through a sub n. So for our proof, we're going to use mathematical induction on n starting at n sub 0 is equal to 2. And so for our basis step, we need to show that p of 2 is true. Well, for n equal 2, the propositional function is for all a1 for all a2, a1 union a2 complement is equal to a1 complement intersect a2 complement. And this is just the original De Morgan's law for two sets, which we proved earlier. So assuming this, then p of 2 is true, which proves the basis step. So if we had not proved De Morgan's law for two sets earlier, we would have to prove it here. So for the induction step, we need to show for all k greater than or equal to 2, p of k implies p of k plus 1. So we'll suppose k is an arbitrary positive integer greater than or equal to 2. Suppose p of k is true. We need to show p of k plus 1. So we suppose p of k, which is for all a1 for all a2 up through a sub k, the union of a1 through a sub k complement is equal to a1 complement intersect a2 complement all the way down to a sub k complement. And we need to show p of k plus 1, which will be for all a1 for all a2 all the way up to for all a sub k plus 1. And then we have the union of a1, a2 through a sub k plus 1 complement is equal to a1 complement intersect a2 complement intersect all the way down to a sub k plus 1 complement. So since p of k plus 1 is a universal statement, to prove it, we'll use a proof by arbitrary element. So we start by specifying the variables. So we'll suppose that a1, a2 down to a sub k plus 1 are arbitrary sets. And we need to show the equality a1 union a2 union down through a sub k plus 1 complement is a1 complement intersect a2 complement intersect all the way down to a sub k plus 1 complement. To prove this equality, we'll start with the left side and show that it equals the right side. So we'll start by grouping the union of the first k sets on the left side. So the left side is a1 union a2 union all the way down to a sub k plus 1 complement, and we're going to group the first k sets together by putting parentheses around them. So this will be the complement of the union shown. And we'll write this as A union B, where A is the union of the first k sets, A1 through A sub k, and B is just AK plus 1. Now, writing the union of A1, A2 through A sub k plus 1 like this, we can view it as the union of just two sets, A and B. And since we then have only two sets, we can apply the original De Morgan's law to obtain this is equal to A union B complement is equal to A complement intersect B complement. And then if we resubstitute what A and B are, this will be A1 union A2 down through A sub k complement intersect A sub k plus 1 complement. So that's after resubstituting for A and B. Now by the induction hypothesis, the union of a1 through a sub k complement is equal to a1 complement intersect a2 complement intersect all the way down to a sub k complement. And so substituting this into the above equality, we obtain the complement of a1 through a sub k plus 1 is the complement of a1 through a sub k intersect a k plus 1 complement. That's from the previous slide. And this will be a1 complement intersect a2 complement intersect all the way down to a sub k complement. That's from our induction hypothesis intersect a sub k plus 1 complement. And we can drop the parentheses and just obtain what is shown there. And this is the right side of the equality in P of k plus 1. And so we've now shown that the left side equals the right side. And so this proves P of k plus 1, which proves the induction step. And since we've proved the basis and induction steps, then by the principle of mathematical induction, for all n greater than or equal to 2, P of n is true. Now here's one more example showing how we can use induction to generalize a formula. So from calculus, the product rule for differentiation states that for any differentiable functions f and g, the derivative of their product is fg prime is f prime g plus fg prime. We want to prove the general product rule for differentiating the product of n greater than or equal to 2 functions. So this is for all n greater than or equal to 2 and for any differentiable functions f1, f2 through f sub n, the derivative of the product f1, f2 times f1 times f2 times all the way down to f sub n is f1 prime, f2 through f sub n plus f1, f2 prime down through f sub n plus all the way down to f1, f2 down to f sub n prime. So the sum on the right side of this formula consists of n terms. In each term, exactly one function is differentiated. In the first term, the first function f sub 1 is differentiated. In the second term, the second function f sub 2 is differentiated, and so on. For instance, when n is equal to 3, the formula is f1, f2, f3 prime is equal to f1 prime, f2, f3 plus f1, f2 prime, f3 plus f1, f2, f3 prime. So the general product rule has symbolic form for all n greater than or equal to 2 p of n, where p of n is the propositional function for all f1, for all f2, down through for all f sub n, and then the formula shown, where the domain for f1, f2, down through f sub n is the set of differentiable functions. Now note again that the propositional function in this statement includes universal quantifiers for the functions f1, f2, down through f sub n. So for our proof, we're going to use mathematical induction on n starting at n sub 0 is equal to 2. And for our basis step, we need to show that p of 2 is true. Well, for n equal 2, the propositional function is p of 2 will be f for all f1, for all f2, f1, f2 prime is f1 prime, f2 plus f1, f2 prime. And this is just the product rule for differentiating the product of two functions, and this is proved in calculus using the definition of the derivative. So we'll just assume it's true for this course. So if we had not proved this earlier, we'd have to go ahead and prove it using the definition of the derivative. Next we have our induction step, and we need to show for all k greater than or equal to 2, p of k implies p of k plus 1. And so we'll suppose that k is an arbitrary positive integer greater than or equal to 2, and we'll suppose that p of k is true. That is, we suppose the formula for differentiating the product of k functions holds. So we then need to show p of k plus 1, which is our formula for differentiating the product of k plus 1 functions. And that's the formula shown. So since p of k plus 1 is a universal statement, to prove it, we use a proof by arbitrary element. So we start by specifying the variables. So we'll suppose that f1, f2, down through f sub k plus 1 are arbitrary differentiable functions. And we need to show the formula, the derivative of the product f1, f2, down through f sub k plus 1 is given by the expression shown. To prove this equality, we'll start with the left side and show that it equals the right side. And we'll start by grouping the first k factors in the product on the left side. So we're starting with the product f1, f2 down through f sub k plus 1 prime. And this is the product of f1, f2 down through f sub k times f sub k plus 1 prime. And this can be written as fg prime, where f is the product of the first k functions, f1, f2 through f sub k, and g is f sub k plus 1. Now on the right side, we now have the derivative of the product of just two functions. And applying the original product rule for differentiating the product of two functions, we obtain our derivative of f1, f2 through f sub k plus 1 is the derivative of fg is equal to f prime g plus fg prime. And this is equal to, substituting for f and for g, this will be f1, f2 through f sub k prime times f sub k plus the product f1, f2 through f sub k times f sub k plus 1 prime. Now the first term on the right side of this equality contains the derivative of the product of k functions. And the induction hypothesis P of k gives us a formula for this derivative. So that's the formula shown from the induction hypothesis. And substituting this into the above equality, we obtain the derivative of the product f1, f2 through f sub k plus 1 is the expression shown. And substituting into the very first term, the expression for the derivative of f1, f2 through f sub k prime, we obtain this. And we can drop the brackets now and distribute, if we distribute the f sub k plus 1 times each of the terms in the brackets, and we'll obtain this expression. And this is the right side of the equality in P of k plus 1. And we've now shown that the left side equals the right side. And this proves P of k plus 1, which proves the induction step. And since we've proved the basis and induction steps, then by the principle of mathematical induction, for all n greater than or equal to 2, P of n is true. Now comparing these last two examples, what you should notice is how similar the two proofs are. Even though the equalities being proved are very different, the steps in the proofs are essentially equivalent. In general, induction proofs generalizing a formula will have a similar structure.